Okay, so tonight we're going to look at the end of chapter 2, and we're going to start with the standard normal distribution. So let's look at what the standard normal distribution is. The standard normal distribution is your normal distribution of your standardized variable. So if I take my variable and I calculate my z-scores here for every data point, okay, then this curve here is for those standardized variables. Remember, when we add or subtract a constant or divide or multiply by a constant, it does not affect the shape. So for the standardized scores to have a normal distribution, the original variable had to have a normal distribution. If it had a skewed distribution, then the standardized scores would have a skewed distribution. Okay, because remember, shape doesn't change. So if I go through and I standardize, or basically if I go through and I calculate my z-score for all of the variables there, then I get this standard normal distribution. And it's the same as what we talked about before when we standardize our scores and we end up with a 0 for the mean, okay, and a standard deviation of 1. Okay, that is going to be our standard normal distribution. This will be helpful to us when we want to find areas under the curve that don't fall nicely into that empirical rule, into that 68, 95, 99.7. We don't necessarily have a z-score of 1 or a z-score of -1. Maybe we have a z-score of 0.2 or a z-score of negative 2.34. Okay, so this is, once we standardize our scores here, then every normal distribution then is the same. If you standardize the normal distribution, every single one is the same. And then we can use either our calculator or the standard normal table to figure out the proportions, which are, again, remember, related to the area under the curve. So we're going to start by looking at what we call Table A. Okay, so Table A is a table. It's in your formula chart. Okay, it's in your formula chart. It takes up 2 pages on your formula chart. On the shrunken one I gave you, it might all fit onto 1. Okay, but Table A is a table of areas under the standard normal curve. Remember, again, once I standardize any variable that is normally distributed, okay, that standard normal curve is going to be the same for all of them. So this Table A will work for any of them as long as you've calculated your z-score. Or you can work backwards and you can use the area to then determine the z-score. So let's look at how this table works. So the table, you will use the left column first. So you'll come down this left-hand side here first. That's where you'll get your tenths place. Okay. If you have, when you look at the table, this is just a small excerpt from the table. You will also see there are spots where it's 1.7 or 2.4 or whatever. Okay. So, but the left is the beginning. Okay. And then going across the top here is where you will find your hundredths place. Okay, and the table where those two intersect will give you an area. And that area is always going to be to the left of z. That's really important that we realize this. You can see this in the purple example over here. Okay, this is what the table shows us. It shows us the area to the left of z. If I wanted to know this area to the right, I would need to take the area I got from my table and I would need to do 1 minus the area I got from my table. Okay, so if I want to do greater than using my table, I need to do 1 minus whatever area is given to me. If I wanted to do less than my z-score, then I can go straight from my table. So as you can see over here on the left now, I've got this area that is shaded. Okay, I have a z-score here of 0.81. So when I'm looking at my table, I find the 0.8 on the left, and then I find the 0.01 on the top. Combine those two and I get 0.81. So my area here, my 0.7910, is this area right here. If I wanted this area over here, I would do 1 minus 0.7910. And that's gonna be dependent upon what it is asking you. Basically, does it want less than or does it want greater than? So looking at that here, you can see this in play. Okay, so I've got a z-score here of negative 0.178. So again, on my zoomed in version of the table, here is my 1.7 there. Here is my, excuse me, my negative 1.7. And then here is my 0.08. So when I put those together, I get my negative 1.78. This is my area here, right there where the two cross. That is my area again to the left. That is my 0.0375. But I wanted to know to the right. I wanted to know what percentage are greater than that. Okay? Remember, the percentage and the area are equal. The area under the curve is equal to the percentage. So if I want to know what is greater than, I need to do my 1 minus 0.0375, which is going to give me 0.9625, or 96.25% are greater than the z-score of negative 1.78. The easiest way you can sort that out as to whether you're looking for, whether you need to do this subtraction or not, is to draw your curve. Shade in exactly what you're looking for. If you shade in to the right, then you need to do 1 minus. Okay? If you shade into the left, then you're good to go. So let's look at an example here that is asking for the proportion of observations between two z-scores here. So find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. So we're looking for this area right here. This is what we're looking for. We want to find the area between them. So if I look at my table, if I use my table A, and I look up my standardized score of my z-score of negative 1.25, that gives me an area of 0.1056. Okay? But remember, my table tells me what's to the left. So that's giving me this little tail right here on the left. When I look at my z-score for the 0.81, okay, that gives me a much larger area of 0.7910. Well, since I just want the area between the two, okay, I can take my 0.7910 and I can subtract this little tail off of it here that I don't want, that 0.1056, and I will end up with 0.6859, or 68.59% fall between those two z-scores. Okay, so you can use your table, okay, to find things that are between as well. Again, though, I think it makes a big difference if you drew your picture. If you don't draw your picture, it can get very confusing as to what it is that you're looking for. Okay, and so what am I subtracting from what, and what is my table giving me? All three of these pictures showed this. These first two here showed what your table was giving you, and this last one emphasized what you actually needed to determine. So what if you were given an area? So if you were given an area, you can work backwards using your table A. So let's say I was given an area of a 0.9, or 90%. Okay, so when I'm given this area here of 0.9, I find in my data table where I get the closest. Okay, so you'll see you don't have a perfect 0.9. Okay, so we went with where you could get the closest, which is 1.2. So I have a z-score of 1.2 and then 8 from the top there. So that would tell me that my z-score here is 1.28. So let's look at some more examples that we have here. So the first one here, we've got using table A in the back of the book, or again in your pink formula chart. In the back of the book, to find the proportion of observations from the standard normal distribution that fall in each of the following regions. It asks you to sketch a normal curve and shade the area representing the region. So for the first one here, we've got Z. We want to know the proportion of scores that are less than a z-score of, so this would be our mean right here, which would be 0, and we want less than a z-score of 1.39. So since I want less than, I'm looking for this here to the left. So I can use my table, okay, and I don't need to do anything else to my table. So remember, when you're using your table, the 1.3 is going to go down the side. The 0.09 will be across the top. Okay, and so where you find those two meet should be at 0.9177, okay, which means that 91.77% or 90.9177 is our area there out of 1. Okay, that is less than a z-score of 1.39. Okay, so looking at the next one. So the next one wants a z-score that is greater than negative 2.15. So again, it asks me to draw my curve. So I'm here, and I draw my curve. Again, I've got 0, negative 2.15 is my z-score, so it's negative, so I'm going to be over to the left. But this time it asks for greater than. So I actually want to go in this direction. So when I read my table, right, my table is going to give me the area to the left. So I'm going to need to do 1 minus. So I'm going to have 1 minus 0.0158, which is going to give me 0.9842, would be this area here to the right. The 0.0158 would be that little area there to the left that we don't want. Okay, and so number 3 here asks us for an area in between. So I've got my curve here, and this is at 0, and it wants the area from negative 0.56 to 1.81. So it wants this area right here. So when I use my table, okay, when I use my table, 1.81 gives me, it'll give me the area to the left of 1.81, which is 0.9649. Okay, and then I can then use my table to find this area right here to the left of my negative 0.56, and then I don't want that part, so I can subtract it off. So my area to the left there is 0.2877. So when I subtract that from my 0.9649, I get an area of 0.6772, which is this area right here in the middle between the two. Okay, so now it's asking us in number 4 here to find the 20th percentile. Okay, well, if you haven't made this connection yet, the percentile is the same as the area under the curve, right? I've been saying 20%, right? So the 20th percentile, 20% of the scores are less than. So if I want to find what's at the 20th percentile, I'm looking for, right, I've got an area here of 0.2. That would be the 20%. So I have an area there of 0.2, and I need to find the z-score for that. So working backwards in my table, when I find an area of 0.2, when I go backwards in my table, that is equal to a z-score of 0.84. Okay. And so the 5th one here, 45% of all observations are greater than z. So I've got my curve. That's kind of a wonky looking curve there. And I want 45% of observations are greater than. Okay, so I need to find not quite 50%, and I want greater than, so I want over here to the right. Okay, and I want to know what this z-score here is. Okay, and so when I find this, basically what I need to do first is I need 1 minus 0.45, which gives me an area of 0.55. I needed that because I need my to the left, right? So now, because my table only shows me what's to the left, so when I go find my table here, that shows me 0.55 to the left, that will give me a z-score of 0.13, okay, which will also have 45% of the points be higher than it. Okay, so when you're solving these problems, these are the things that you're going to need to do to make sure that you are receiving full credit when you do these. So the first thing, you need to state the distribution and values of interest. Draw your normal curve, shade your area that you're interested in, okay, and identify the curve. Remember to identify it. So when I draw my normal curve, right, normal, let's say this is my normal standardized curve, mean of 0, standard deviation of 1. Remember, that's what is in our parentheses there, is the mean and the standard deviation. Okay, show whatever it is that you're interested in. So shade the area of interest and clearly identify your boundaries. If you know your z-scores, write them down on there. If you know your area, write your area down. Okay, basically put all the information that you know, okay, into a sketch or into a sentence. Okay, your next step then will be to perform your calculations and to show your work. Okay, so you either need to show your work for all your z-scores and then use table A, or you show your work for your technology, and we'll talk about technology in class for these. I think that will be a little bit easier. And then make sure you actually answer the question, and if there is context, go ahead and put it in context. So let's look at this example here. I went ahead and put the whole solution out there so that you could kind of follow along and you can see what they mean by getting all of that information out there. So this question here is about Tiger Woods and golf, and it wants to know what percent of Tiger's drives travel at least 290 yards. So basically it wants to know which ones are bigger than 290 yards. So you were given this curve right here that he had. It's a normal distribution. You were told it's a normal distribution. You were given the mean. You were given the standard deviation. So when they draw the curve, there's your mean of 304. Okay, you notice this is 312, which is standard deviation of 8. 320. Right, it's an appropriately drawn curve. It's labeled right here with our capital N, and then in parentheses we have the mean and then the standard deviation. And this curve is shaded. We're looking for greater than, because we're looking for at least 290 yards. So we shaded what we wanted. Okay, we marked 290 yards where that would fall here on the curve. Okay, and they went ahead and they put the z-score out there already, that it's negative 1.75. And so step 1, where we're stating the distribution and the values of interest. Okay, you can restate that. Okay, you can restate what it wants. You can also, like I said, draw that picture, which that picture is such a big deal. It will really, really help you make sure that you are not making any mistakes. Step 2, you've got to perform your calculations. So in step 2 here, if we wanted to find this, right, we would find our z-score, which is negative 1.75, right, 290 minus the mean divided by the standard deviation. So we would find the z-score, okay? We would use our table, and we would have 1 minus, since we want greater. Okay? And so that would translate into about 96%. Again, we will talk about how this looks under the calculator later. And so then you need to actually answer the question. And you'll notice it's in context. About 96% of Tiger Woods' drives on the range travel at least 290 yards. Okay, so let's look at this one. So this one wants to know what percent of Tiger's drives travel between 305 and 325 yards. So like always, the first step would be to state the distribution and the values of interest. So we've drawn the curve here, labeled the curve, marked off the area that we're looking for, and we marked those values, 305 and 325. So we went ahead and we marked those values out so we knew exactly what we were looking for. So in step 2 then, we need to perform the calculations. And remember, you always, always need to show your work. Okay, so if I'm going to find my z-scores here, my z-score of 305 would be 305 minus 304 over 8, which is going to give us 0.15. And then my z-score of 325 would be 325 minus 304 over 8, which is going to give us 2.63. Okay, so you can go ahead and draw this out. right? I can go ahead and draw my standard normal curve, right? So my standard normal curve now, whoa, that's terrible. So my standard normal curve, right, putting my mean here at 0, and I have a 0.15 and a 2.63, so like way over here, 6, 3, and so we're looking for this area right here. So when I use my table, okay, so when I use my table, I find that the area to the left of 2.63, the area to the left of 2.63 is 0.9957, and then the area here to the left of 0.15 is 0.5517, and I want to subtract that off because I don't want this area, I just want the area here in between, and so I get a total then of 0.4440. So I show all of my work, and then I need to actually answer the question. So in answering the question, about 44.4% or 45% of Tiger's drives travel between 305 and 325 yards. So I put it in context using my boundaries that were set up in the problem. If you're going backwards and you're using, you're given an area and you're using that area to calculate a z-score, the same steps need to be followed. We need to state our distribution, draw your picture, label it, identify it, put your boundaries in, shade the area under the curve. Okay, perform the calculations. You'll notice your technology command is a little bit different here. Again, we'll look at that in class. Okay, and then actually answer the question. So looking at this example here, high levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with a mean of 170 milligrams of cholesterol per deciliter of blood and standard deviation of 30 milligrams per deciliter. So the question wants to know, what is the first quartile of the distribution of blood cholesterol? So again, the first thing we need to do is draw it out and identify it. So this time we want to know what the first quartile is. So we want to be able to know what number that is that falls there. So we're looking for the area of 0.25. Okay, so we go ahead and we sketch that curve out. I label our curve. Normal, 170, mean of 170, standard deviation of 30. Okay, I shade what I'm looking for here. Okay, and I can use my table now to work backwards to find out what that z-score is. And then once I know that z-score, I can go back and I can find the actual data point that is there. So working backwards to find that z-score, I use my table to find 0.25. And when I find 0.25, that correlates to a z-score of about negative 0.67. Okay? So when I plug that back into my z-score equation, negative 0.67 equals my data point minus my mean of 170 over 30. And now I solve for x. X is equal to 149.9. So that tells me, and then I need to write my sentence in context now. The first quartile of blood cholesterol levels in 14-year-old boys, again, we have to have that context. We're not talking about all males. We're talking about a certain range. We're only talking about males. So for 14-year-old boys, is about 150 milligrams per deciliter, or 149.9 milligrams per deciliter. And so you could go backwards as well using those exact same steps. So we're going to go ahead and we'll stop there, and we'll look at the technology of how to do this on your calculator in class, as well as how to assess to determine if data is normal or not, because that's also going to be done on your calculator.